All right, welcome to AP Chemistry. We're looking at Unit 1.5. In this problem, we're looking at question 10 of this assignment. And it states that we are looking at atomic radii of elements in the same period. We should know periods are the horizontal rows found on the periodic table. And so when we have elements found in the same row, what we have to do is maybe compare those for the size of the atom. And then as we move forward and we look at periodic trends, we're going to be looking at ionization energy and things of those sorts. And we have to understand how we can explain those in terms of Coulomb's law and that type of thing. So it says, which of these species has the smallest atomic radius, sodium or magnesium? And then provide a detailed explanation for your choice, explicitly referencing Coulomb's law. Now, in my picture here, I am showing not only sodium and magnesium, but I'm also showing chlorine to help further the explanation. Not that you need to mention chlorine in your explanation. Of course, we're looking at Coulomb's law, and we look at Coulomb's law, and this is the equation that we're given from AP, and it's just basically showing us a proportionality, showing us that the force of attraction between charged particles, and in this case, what we're looking at is the force of attraction between the nucleus and the valence electron. So for sodium, we have 11 protons in the nucleus, and its valence electron way out here. What we're looking at is the overall force of attraction, knowing that it is going to be a force of attraction because protons have a positive charge and electrons have a negative charge. And so opposite charges attract. We also talked about repulsions and electron-electron repulsions in electron shielding, but that is not something that we are going to mention when we talk about period trends, because we're going to notice that every one of these atoms in a period have the same number of core electrons, and so the shielding effect does not increase with added electrons. And so the theme of this movie, if you want to call it, is nuclear charge. All right, so anytime we're dealing with a period trend, the theme you should be spouting off is nuclear charge, and that is going to be our theme. Remember, our theme for group trends was the added energy levels and also electron shielding. For a period trend, the only thing that you should be thinking about is nuclear charge. All right. And so we look at sodium, and what we want to do is we want to see, we see, first of all, that each of these atoms have the same number of energy levels. They each have 3 energy levels. We can see that in the Bohr model. We can see that in the electron configuration. And so we're not going to consider radius here as far as Coulomb's law, but the force of attraction between the nucleus and the valence electrons is going to affect the radius. And so because we know that there is a direct relationship between the nuclear charge and the force of attraction between the nucleus and the valence electrons, a direct relationship. And so what we have to figure out is what is the effective nuclear charge. Now, we noticed when we had group trends that as we went down a group, and our last example was magnesium and calcium in the previous problem, we noticed that the effective nuclear charge did not change, even though there were added protons. And that's because there was more core electrons as we go down the group that affects the overall effective nuclear charge. Here, we're going to see that each of these atoms have the same number of core electrons, but a different number of protons. How does that affect the effective nuclear charge? So let's go ahead and look at that. So if we look at the effective nuclear charge of sodium, and we know that the effective nuclear charge is equal to Z minus S, and Z is equal to the number of protons. So here, the number of protons in sodium is 11, and we're going to subtract the number of core electrons, S. And so we look at core electrons. Now, in this picture, you can either use the Bohr model to count core electrons, or you can use the electron configuration. If we use the electron configuration, I have the core electrons, and core electrons are electrons that are not valence electrons. I have that outlined in blue. So we have 2, 4, 10 electrons, or you could count 2, 4, 6, 8, 10 electrons from the Bohr model. So 11 minus 10 is equal to 1. So sodium has an effective nuclear charge of 1. And so I'm just saying this is equal to 1. The effective nuclear charge is equal to 1. All right. So just putting that below it. So you need to know ZEF equals 11 minus 10, which is equal to 1. You might also notice that sodium is in group 1. And so it has an effective nuclear charge of 1. Very interesting that we can see that. When we go to magnesium, and we look at its effective nuclear charge, and this is what we're comparing in this assignment here, is sodium and magnesium, we're going to notice that magnesium has 12 protons. So we're going to put this in here. It has 12 protons, equals 12 minus how many core electrons? It's the same number of core electrons in each period. It's 2, 4, 10. You can still count them right here. So while the number of valence electrons changed, the number of core electrons remain the same. And so that's still 10, and 12 minus 10 is 2. So the effective nuclear charge of magnesium is higher than the effective nuclear charge of sodium. And what we're saying in Coulomb's law is that the force of attraction between the valence electrons and the nucleus is directly proportional to the effective nuclear charge, and that's what we're going to say this. And so we can say if the effective nuclear charge is 1 in sodium and 2 in magnesium, well, then we can say that the force of attraction between the valence electrons in magnesium is greater than the force of attraction between the valence electrons and the nucleus in sodium. Do you see that? And we have a quantitative way of doing that. Now, as we go across a period, we notice that the number of core electrons always remains the same, but the number of protons increases. So when we get to something like chlorine, even though we're not asked about it here, we can see that we're going to keep the same number of core electrons. It's going to be the same number, 10, but we have 17 protons minus 10, and what we end up with is an effective nuclear charge of 7. And I don't know why that's orange, but there it is. So that's why we can say the effective nuclear charge increases as we go left to right across a period. So as we go from sodium, look at your periodic table. As we go from sodium to magnesium, the number of protons changes, but the number of core electrons remains the same. So we see that the effective nuclear charge increases as left to right. What does that mean for the force of attraction? It means moving left to right across a period, that the force of attraction that the valence electrons feel for the nucleus is greater, right? And what does that do to the size of the atom? So now we're looking at all these atoms having the same radius because they have the same number of energy levels. But wait, there's a force of attraction at play because there is a larger nuclear charge. The force of attraction is greater between the nucleus and those valence electrons, and so those electrons are pulled in a little bit closer to the nucleus, making it what? Smaller. You see that? So magnesium would be smaller than sodium. Why? Because it has a higher nuclear charge. It has more protons. By the way, what are the particles in the nucleus? They're protons. All right, the only charged particle. And so we can even see if we were comparing magnesium and chlorine, we see that chlorine has a higher effective nuclear charge. It has more protons, has the same number of core electrons. Therefore, the attraction between these valence electrons and its nucleus is greater, and it pulls that electron, pulls those electrons in a little bit closer to the nucleus, making it smaller. All right, so that's the idea. Now, what does that look like as far as a written explanation? Let's go ahead and take a look, and let's see if we can put this into words and make sense of it and see how that matches our picture. So if we notice, I asked which of these species is the smallest, and what did I start off with my answer? Magnesium has the smallest radius. Is it any wonder what my answer is? Is anyone questioning that I think magnesium has the smallest radius? No. So anytime you're asked whether or not which species is the smallest or which substance is the largest, answer the question first and then go into your explanation. So magnesium has the smallest radius. So sodium and magnesium are in the same period and have the same number of energy levels. Did I see that in my picture? In my picture, I notice that sodium and magnesium, I first of all can find that on my periodic table that they're in the same period, but they have the same number of energy levels. Notice 1, 2, 3 energy levels, or if you look from the Bohr model, 1, 2, 3 energy levels. 1, 2, 3, 1, 2, 3. So they're in the same period. They have the same number of energy levels. All right. The next thing that we're going to look at as far as my statement, it says, however, magnesium has a what? A higher effective nuclear charge due to having a larger number of protons. Okay, this is a big deal. So the two things have to go together. It is not just having more protons, it's having the same number of energy levels, which means it has the same number of core electrons and more protons. So we notice magnesium has more protons, but it also has the same number of energy levels. What does that mean? It means that the attraction, or the force of attraction, is going to be greater between the valence electrons and the nucleus in magnesium than in the valence electron and nucleus of sodium. And so that's what we're looking at there. And so, however, magnesium has a higher effective nuclear charge due to having a larger number of protons. According to Coulomb's law, the force of attraction is directly proportional to the nuclear charge. So we see the effective nuclear charge in magnesium is greater than the effective nuclear charge in sodium. So we know that the force of attraction between the valence electrons and the nucleus is greater. How does that affect the radius? So since magnesium has a higher nuclear charge, the force of attraction between the nucleus and its valence electrons is stronger. And if that force of attraction is stronger, it's going to pull those valence electrons or all of those electrons in closer to the nucleus, making it have a smaller radius than sodium. And so we went through our entire picture. Our picture matches the statement. And again, what is our theme? Nuclear charge. And we notice if it has a higher effective nuclear charge, that it was a smaller radius. Notice I have that bolded. And if the effective nuclear charge were lower, the radius would be what? Larger. And so we understand the relationship between the nuclear charge and the force of attraction. And that's basically how we're using Coulomb's law to explain the differences in size of sodium and magnesium. Hopefully this helps you answer that question. For now, thank you for watching. Please like and subscribe.